My name is Goyong, and today I'm going to briefly explain about our project, DSP project. So the first task is involving simulating this signal, and we need to design a FIR filter using Python. So for Python, first of all, for me, my preference is using virtual environment VNF. So for let's say we need for starting, you can just use the tools and start and to verify our pip installed. So we can use pip list, and here are our install packages. So for this code to run. So next up, so this is the original code, and this is our uh, filter. So we need to use SciPy, and we need to calculate. So for me, for this design, I use 51 for better better gain, better SNR for the next task too. But originally I used 31. 51 is also okay. So this is a function to calculate. Set it is same as the original and continue, and this is our design. So for our design, we designed this filter using bandpass filter and using the SciPy functions. The function is set about 9 megahertz to the low cut frequency is 9 megahertz. The pass band low cut and stop band is this one. But this one we ignore first, and then this one we apply the filter. We save. This is important. We need to save the coefficients into a text file for us to use in the C++ later on. This is just the main execution. We use this to call the function, and it will generate the required code. This is the plotting. So our result is like this. Here is the input signal and output signal, the clean signal versus the filter signal. So we can see that the green one is the noisy signal, and after the filter, we can see that it is more uniform. And this is the filter response. And next up, after this, we get the text file. This is the coefficient. We need to adapt it later, and this is the raw signal data and the clean data. So for task 2 is is similar to class 1, but in C++ environment. So I just directly use the Vitis to simulate. So first of all, we need to design a HFAR. We use the HFAR because we need to simulate it in a test bench separately. So using HFAR, we can just call the HFAR. It's similar to import in Python. So we continue. So we read this data and we calculate, we adapt it similarly from the Python, but in C++ and verify. And hence, we can, after this, we need to compile using this one, sorry, I cannot get the place cam. So this one is, we need to compile our executable as per test bench and test bench CPP. This is the target. This is the original. This is just a setup. So after compile, it's okay. Then we need to call the function. After this, we can verify the result that we get. So we can first of all we load the input signal, calculate the input, load the 51, apply to all samples and calculate. This is just the debug stage, and we verified that the Python and the output match the specs of over 20 dB attenuation. The output, more than 20 signal to noise ratio. I think that's all. I think for task 3, I'll pass to Arif to explain. Thank you.
Hello everyone, today I will show you how to design and optimize a digital FIR filter using VITES and also Vivado. So our goal is to filter a 10 MHz sine wave. So let's start with the task 3, the HLS baseline synthesis. In VITES, my initial code is to standard float data type. So we move before we move to the synthesis and also post simulation. So we need to use a C simulation first to check if our filter pass the SNR output. So you can see here the filtering is complete. So our output SNR is past the SNR, which is at 21.28 dB. So next we move to run the C synthesis to show their report and performance. So the synthesis was finished. So we need to see their report, their performance. So as you can see here, there is a timing performance, which is a estimate clock, and latency, which is high, and also since we use a float data type, so the DSP and also LUT, which is used, is high. So for next, we're gonna do for CRTL co-simulation. So now after the co-simulation was still running, so if we go into the Vivado to show their waveform output. So now the run is complete. So it shows that our RTL design is successful. So you can see here. Now we exit the Vivado, and then for CRTL simulation was finished successfully. So we can see the report here. So it shows the information, general information and performance and resource estimates. Shows that the latency is high and also total execution time. So that's the task 3 is done. So next we move to task 4. Now we move to task 4, implementation and power analysis. So first I open our project in Vivado. So after we export our sources, which is contain RTL file, so and also IP file, so we can run the synthesis first to see before we run the implementation to see the power reports. So now the synthesis successfully complete, so we run the implementation. So the implementation successfully complete, so we can open the implemented design. So after we open the implemented design, so we can generate plot networks. And also we have a tool for the timing constraint. So which is we generate our clock first before we run our power straight away to the click this for the report power. We can see the total on-chip power. So we can showing both dynamic and static power usage for our baseline design. So that's it for our task 4. So next we move to task 5 for the optimization. So now we are on the task 5, which is optimize FIR filter. So you can see our code. We use a fixed point data type and also HLS pipeline, HLS array partition is also HLS unrolled. So now we need to see if our filter matches its pass SNR, which is more than 30 dB. So let's get started. So now our simulation test bench is complete. So filtering is complete. So our output is still pass, which is in value 21.28 dB. So which is done with zero errors. So next we will look at the report and also performance analysis. This is our report, which is the timing and somebody the estimated is less to 4.225 nanoseconds. So this the latency between becomes zero because the pipeline time is yes. And then we look at the DSP and LET. So the utilization is not too much as earlier before the optimization. So you can see the output waveform comes in slightly different with the previous one. And the C synthesis is also can generate our RTL file. So we can see on the Vivado next. So for the Vivado, we do it the same. So we generate the report power analysis. After we doing create the clock and also report timing summary. So you can see that there's a dynamic and static power. So we can see how total chip on power. So there's slightly difference between the optimized and the baseline. So we can achieve that successfully. So that's it.